By now, we have seen that a qubit state can be represented in the computational basis, or equally well in any other orthonormal basis, such as the plus-minus basis, or in the case of two-qubit systems, they can also be represented in the Bell basis. While going through the protocol for superdense coding, we have seen that Bob can transform the Bell states into the computational basis states by doing quantum operations on the system. In this lecture, let's take another look at how different bases are related to each other and how the representations of quantum states in these different bases can be related to each other. We have wrote down the generic qubit state psi as alpha 0 plus beta 1. And now, how can we write psi in the plus-minus basis that is expressed as a superposition of the plus-minus states? We already know that the plus state is 1 over square root 2, 0 plus 1. And the minus state is 1 over square root 2, 0 minus 1. From this, we can work out that 0 state is actually 1 over square root 2 plus state plus minus state. And the 1 state is 1 over square root 2 plus state minus minus state. With this, we can now substitute this back into an expression for psi that we would have alpha 1 over square root 2 plus minus plus beta 1 over square root 2 plus minus minus. This is just 1 over square root 2, the term alpha plus the term beta that goes with the plus state, and 1 over square root 2, the term alpha minus beta that goes with the minus state. So if we want to write down a column to represent this particular state in the plus-minus basis, we can also write this as 1 over square root 2 alpha plus beta and 1 over square root 2 alpha minus beta. And then we have to remember that this is in the plus-minus basis. Previously, we have seen that for a single qubit, we will represent this as a column of alpha beta, which is in the computational basis. To avoid confusion, throughout this course, whenever we encounter columns or rows and matrix representations of a physical object, we would use the computational basis rather than the other basis. Now, how about the basis transformation for two-qubit system? For simplicity, let's just take one of the Bell states, psi plus state, for example. This can be written as 1 over square root 2, 0, 1 plus 1, 0 in the computational basis. Can we now express this in the plus-minus basis? That is in the basis of plus plus, plus minus, minus plus, and minus minus. We recognize that for each of the two terms is actually a product structure. So we can do the basis change of zeros and ones separately for each of the terms using what we have seen previously. So this can be now written as 1 over square root 2. For the first qubit, the 0 state, we write it as 1 over square root 2 plus plus minus. And now for the second qubit, which is in state 1, this is 1 over square root 2 plus minus minus. And we do the same for the second term. And now let's just work out the terms. We have a square root 2, second square root 2, and the third square root 2. So this gives us 1 over 2 times square root 2. What is inside the bracket? We have this plus plus term and add on to another plus plus term. So we have 2 plus plus term. And then the plus minus term goes with the minus sign here. The plus minus term goes with the plus sign here. They cancel out. The minus plus term goes with the plus sign here. And it goes with the minus sign here. So they also cancel out. Finally, we have the minus minus term goes with the minus sign here. And it also goes with another minus sign here. So we have minus 2 minus minus, which is 1 over square root 2 plus plus minus minus minus. By now, you should be able to recognize that this is in the form of another Bell state, namely the Bell state phi minus in the plus minus basis. So it's not saying that the psi plus state is equivalent to the phi minus state. It's just saying that this phi plus state represented in the computational basis, if we represent it in the plus minus basis, it will have the form of the phi minus state in the computational basis. Okay. As we have mentioned previously, Bell states are the maximally entangled states. So we see that by doing this basis transformation, entanglement is kept. So there's no change of entanglement. This must be the case because here we're not changing the state, we're just changing the representations of the state. So as quantum correlation, the entanglement must be kept. Next, let's find out how to carry out this transformation of basis representations more generally. Suppose we have two different sets of bases represented by A and B. So in the A basis, we have kept A1, A2. In the B basis, we have kept B1 and B2. The question is to find the transformation from the states in the B basis to the states of A basis. If we denote this operation by U, B to A, when this operator acts on the row of states in the B basis, that is, it acts on the row of B1 cat, B2 cat, it should give us the row of states in the A basis. So the general form of this operator should be U B to A. That is a cat A1 times a bra B1 plus cat A2 times a bra B2. More generally, we can also write this as a summation of index j equals to 1 and 2, denoting the indexes of cat A and cat B. And then we have the cat AJ with the bra BJ. Okay? And what is the Hermitian adjoint of the operator U? So U, Hermitian adjoint, is then if we use this form, the summation of the index j, and we will then have the cat bj and the bra aj. So this is actually the transformation from the A basis into the B basis. So this is A to B. Okay. How about the product of U and U adjoint? So this is a transformation from the B basis to the A basis, and then times the transformation from the A basis to the B basis, which should go back to the B basis. So this operation does nothing to the quantum state. That is, it is identity. So from this, we can recognize that this operator U, B to A, is actually a unitary operator. That's actually why we denoted by U, U for unitary. This change of basis can be extended to arbitrary dimension. Now, suppose we have a quantum system of dimension n. In this n-dimensional quantum system, we have two different bases, one denoted by A, that has the basis state A1, A2, and AN. There's another basis B, denoted by B1, B2, and Bn. The basis change operators would work exactly the same as in a qubit system. So if we have the unitary operator that change the basis state from the B basis to the A basis, it should be in the form of the summation of index j goes from 1 to n, the cat a's, and the bra b's. In the special case of a 2-qubit system, if we have two bases that can be written as tensor product of the subsystems, that is to say we have a basis A prime that can be written as their state in the first qubit, tensor the state in the second qubit. And similarly, we can have a basis B that also have this tensor product structure. Then the basis transformation operator, U, goes from B prime to A prime, also inherited this tensor product structure. That is, we can write this as a U of change of basis from B to the A basis and tensor the operator on the second qubit. Now we can transform the states in one basis into another basis. How about the representation of the state into this basis, which are given by the complex coefficients? We can write down the state psi in the A basis with complex coefficients alpha 1 and alpha 2. We can also write it down as a linear superposition of states in the B basis with the complex coefficients beta 1 and beta 2. How do we relate these two columns of coefficients. First, let's recognize the coefficient alpha 1 as the inner product between the ket A1 and state psi. And the coefficient alpha 2 is the inner product of A2 and the state psi. So we can write this as the column of brass A1 and A2 inner product with the state psi. Similarly, the coefficient beta 1 and beta 2 are also the inner products as such. So this can be written as a column of the brass, B1, B2, and take inner product with psi. So now, rather than transforming the cats into cats, we need the transformation of the brass into the column of brass. Upon recognizing that the column of the brass is actually the permission conjugate of the row of cats, and we have this expression, so we can write this column of brass and take the permission conjugate of the left-hand side of this expression. This would give us the column of brass, but the B basis. And then the permission adjoint of this U operator. And since we want something from the B brass to the A brass, we can multiply the unitary operator again on the right-hand side of this expression so that we would have an identity here. So this gives us the brass of the B basis is given by the brass of the A basis multiplied by the unitary transformation from B basis to the A basis. And now let's see what we can do for this column of complex coefficients. The column beta 1, beta 2 is this column of the brass multiplied by the state. So we can write this as brass A1, brass A2, the unitary operation, and now we have state psi here. We know that state psi is actually given by the row of cats multiplied by the column of coefficients. So this is and now we would have the row of cat A1, A2 multiplied by the columns of the coefficients alpha 1 and alpha 2. So given alpha 1 and alpha 2, we can get beta 1 and beta 2 by evaluating this matrix. So this is actually our transformation matrix. The transformation matrix between the representations of state in the A basis and the B basis. We can also work out what is the element of this transformation matrix. For example, its first entry is a bracket A1, the unitary operator, B basis to A basis, and the ket A1. So now we can use this expression that we have worked out earlier and recognize that this is just the bra B1 inner product of bra E1 and cat A1. Similarly, now we can work out other entries of this transformation matrix. So the first entry is just B1 A1, and the second entry would be B1 A2. This is then B2 A1, and the last entry is B2 A2. So this would be the transformation matrix that would relate the column vectors in the A basis to the column vectors in the B basis. Now let's apply what we have learned for the general formalism of change of basis to our previous examples. We have two bases. One is computational basis, the other is the plus-minus basis. And the cubic state psi can be expressed as a superposition in the computational basis or a superposition in the plus-minus basis. We want to find what is beta 1 and beta 2 given alpha 1 and alpha 2. And we know that this can be done by the unitary operator that transforms the states in basis B to the states in basis A. So this operator is in the form of cat 0 bra plus cat 1 bra minus, as what we have worked out previously. And what is this operator in the matrix representation? So the cat 0 is the column 1, 0. Bra plus is the row 1 over square root 2, 1, 1. Cat 1 is the column 0, 1, while bra minus 1 is the row of 1 over square root 2, 1 minus 1. And we just need to work this out, and we would find out that this is the matrix 1 over square root 2, 1, 1, 1, minus 1, which is exactly what we call the Hadamard matrix. As we have claimed previously that the Hadamard operator changed the basis of 0, 1 into the plus-minus basis, and vice versa. We can also work out this matrix with the other form that we have seen previously. That is to say, UB into A is given by the inner product of plus 0 plus 1 minus 0 minus 1. The inner product of plus and 0 is 1 over square root 2. So we get 1 here. The inner product of plus and 1 is also 1. The inner product of minus and 0 is 1, but the inner product of minus and 1 has a minus sign. So this is again the Hadamard matrix. So now we can work out the column beta 1, beta 2 as this matrix, the Hadamard matrix, 1 over square root 2, 1, 1, 1 minus 1, multiplied with the column alpha 1, alpha 2. This would give us 1 over square root 2, alpha 1 plus alpha 2, alpha 1 minus alpha 2. That is to say, we can now write out our state psi, which previously was alpha 1, 0 plus alpha 2, 1, as now 1 over square root 2, alpha 1 plus alpha 2, cat plus 1 over square root 2, alpha 1 minus alpha 2, cat minus. We can now apply this formalism to higher dimensional system. The example that we have seen previously was to represent the 2-qubit Bell state psi plus in the form of 1 over square root 2, 0, 1 plus 1, 0 in the plus minus basis. And let's now see how we can do this with the general formalism. That is to say, we want to find its transformation given the representation in the computational basis and what is the representation in the plus minus basis. So this is now our basis A, and the plus minus basis is our basis B. The first thing that we recognize, what is also we used previously, is that this A basis is actually a tensor product of the basis in the subqubit. So this is state 0, 1, tensor with 0 and 1 in the second qubit. And the B basis also have a tensor product structure. So this is plus minus basis for the first qubit, tensor plus minus basis for the second qubit. We have seen previously that if we have such tensor product structure for the transformation of basis, the operator U that gives us the transformation between the B basis and the A basis would also inherit this tensor product structure. We already know that the transformation between the computational basis and the plus minus basis is given by this U operator, which is the Hartmann matrix. So this can be written as the Hartmann matrix tensor, the Hartmann matrix. If we work this out, we will find that this is 1/2, 1, 1, 1, 1, 1 minus 1, 1 minus 1, 1, 1 minus 1 minus 1, 1 minus 1 minus 1, 1. So this 4x4 matrix would give us the transformation between the coefficients in these two different representations. Let's see how we get it there. So now the column of the complex coefficients in this computational basis for psi plus is 1 over square root 2, 0, 1, 1, 0. And we apply the basis transformation U. On top of that, this will give us this matrix multiplied by this column, which is then 1 over square root 2. I will skip the work, but you can work it out yourself. This is 1, 0, 0, minus 1. That is to say, the state psi plus, now written in the plus minus basis, would have plus 1 for the plus plus cat. So we have 1 over square root 2 plus plus. And it does not have any elements of the plus minus and minus plus cats. And the last term, the minus minus, goes with the minus sign. So this is minus 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 state. And this is exactly the expression that we have found previously. Of course, not all change of basis in a composite system can be decomposed as tensor product of the change of basis in its subsystems. In fact, most of the basis transformations cannot be done this way. Let's take the Bell states, for example. We have seen that this Bell basis is also a good basis for the 2-qubit system. And what is the change of basis operator between the computational basis and Bell basis? We can just follow the recipe that we had worked out in general and find out the matrix representation of this change of basis transformation from the B basis to the A basis, which is given by this 4x4 matrix. Now, we also remember that we have done something very similar when we talked about superdense coding, that by doing operation of C0 followed by a Hadamard gate on the first qubit, we transform the Bell basis into the computational basis for decoding. So if we work out the matrix representation for this operation, it is given here. Now compare this matrix to the matrix above, we will find that they are not the same. In fact, is the second row and the third row are swapped. This is because in the superdense coding, we transform psi plus into 0, 1 instead of 1, 0 in this basis transformation, and phi minus into 1, 0. So there is a swap of basis between this B basis and the basis we have for the superdense coding. In this lecture, we find out that states in one basis can be related to states in another basis by a unitary operator. We have also seen that the representations of quantum states in different bases are related by the matrix representations of that unitary operator. In the next lecture, we are going to explore yet another important result of quantum information, the no cloning theorem.